Last sessions, I explained the reasons why the equation to solve the stellar structure is quite difficult to solve. First, try to simplify the equations for the stellar structures is the polytropic models. So I'd like to explain the polytropic models first. If the pressures of a stars were only a function of the density, so pressure is the only function of the density. So we could pick up just only the first two pairs of the equation, hydrostatic and the continuity. These two equations we only need. Then we could find out the stellar structures. This is the simplest case, find out the stellar structures. So I'd like to explain this case. So from the first equation, this hydrostatic, you can write that this is minus r squared over rho round r, round p, round r equal gm. Then you can find the derivatives, the both sides. G round m round r. Then you can substitute round m round r here. Then you will get these equations. So these equations can be obtained by the combination of these two equations, hydrostatic and the continuity equations. Okay, then we'd like to introduce the polytropic equation of state. So polytropic equation of state, the equation of state with the following form is called the polytropic equation of state. So P is only the function of density, and the density and the power index of the density is expressed as gamma. Gamma is 1 plus 1 over n. This n we call the polytropic index n. So sometimes you might think that this is just artificial equations. We don't have such an equation in the real physics, but it's not true. When we study the completely degenerate electron gas, this case is the pressure is expressed as a function of the density alone. In that case, the gamma becomes 5 over 3. So in this case, you can just substitute this is gamma is 5 over 3 to find out the n. It becomes 1.5. Okay? For the relativistic degenerate electron gas, is a gamma is 4 over 3. So in this case, is n equals 3. And also we have studied adiabatic case. Adiabatic case corresponds to the convection responsible for the energy transfers inside of the stars. This is also, we express that P is a proportional to rho to the gamma. Polytropic equation of states is a fully convective stars, or star is composed of the completely degenerate electron gas, or relativistic degenerate electron gas. So P is a proportional constant K times rho 1 plus 1 over n. You can find the derivative. P with respect to R. This becomes K. N plus 1 over n. Rho 1 over n. Round rho, round R. You can multiply R squared over rho, round P, round R. It becomes K. N plus 1 over n. R squared. Rho 1 over n minus 1. Round rho, round R. Then these equations, you can substitute these equations. 1 over R squared. Round R. R squared, rho, round P, round R, equal minus 4 pi 0. So you can substitute here. It becomes 1 plus n k over 4 pi g n 1 over r squared d dr r squared rho 1 minus 1 over n d dr. So now independent variable, just only the r. So we change from the round to the d equal minus rho. So dependent variable is just only we have rho. And the independent variable is r. The equation, structure equations becomes this one. This is exact same equation that I showed. So we need to solve these equations. The solution rho called the polytropes. The two boundary conditions are required. First one is the density is 0 at the r equal r because the pressure is 0 at the surface of the studs. Actually there is no gas, so density is 0. So at the r equal 0, this is at the center, this point, at the centers. dp dr is expressed as minus rho gm over r squared. At the centers, actually mass is 0. So dp over dr is 0. So this means the density gradient has to be 0. So we have two conditions, but still 2 point boundary condition. This is still points. So this means r equal r and r equals 0. 2 point boundary condition is given. So substituting the following equation to structure equation, theta and g are dimensionless variables. So rho is expressed rho sub c, theta to the n. And the theta is changing from 0 to the 1. The 0 corresponds to the surface. Because if you substitute the theta equals 0, so it becomes rho equals 0. Theta equals 1 corresponds to the center, because density is equal to the central density of the rho sub c. And the r is expressed alpha times g. Alpha is expressed in this equation. So alpha has the dimension of the meters. So equations becomes expressed this one. So by introducing the g and the theta, maybe I can show you how to get this equation. R squared over rho to the n minus 1 over n d rho dr is expressed r squared rho sub c n minus 1 over n theta to the n minus 1 and n rho sub c theta to the n minus 1 d theta dr. We substitute this expression to the rho. So you will get this expression. It becomes equal to r squared rho sub c power index 1 over n n d theta dr. Theta to the n minus 1 is going to be cancelled out. Then we can back to the equations. 1 over r squared d dr r squared rho to the n minus 1 over n d rho dr is expressed rho sub c 1 over n n 1 over r squared d dr r squared d theta dr. Then back into the original equations. It's 1 plus n k over 4 pi g n rho sub c 1 over n n over rho sub c 1 over r squared 1 over r d dr r squared d theta dr equal minus theta to the n. Then n is going to be cancelled out. And then we name this part alpha squares. R is expressed alpha z. So it becomes 1 over z squares d z square d theta d z equal minus theta to the n. So we get the equation. We call that this is Lane-Emden equations. Okay, we obtain this equation. And the boundary conditions at the z equals 0. So this corresponds to the r equals 0. The derivative is becomes 0. So this is exactly equal to this derivatives equal 0, r equals 0. But really big difference is here. We consider the density is 0 at the surface of the stars. But by introducing the thetas at the center, theta is 1. So this is quite big difference between the last cases with the present case, because this is 1 point boundary condition. 1 point means r equals 0. Then by solving these equations, actually we could find these structures of the polytrope. So at the n equal 1, this is structures. At the n equal 2, you can find these type of the structure. So density is concentrated at the centers. At the n equal 3, density more concentrated at the centers. Analytical solutions are given at the n equals 0, 1, 5. So these n equals 2 and 3s, we have to use a numerical simulation to solve the differential equations. I'd like to show you another important quantity, such as the total mass or radius in the laters. So our polytrope on the index 3's mass is concentrated at the centers compared with n equal 1 and n equal 2. The polytrope on index 1 is a more even mass distribution can be discovered by looking at these figures. This is the end of this session.